Okay, this is chapter 8. We're going to start now the design of floor systems. And so the first video is going to be about designing your one-way slabs. And then we will talk about the T-beams. So those are interior beams that you have in your project, right? And then, of course, we're going to move into joists, no? So you have joists, okay? All right, so those are probably going to be the 3 videos on this lecture. So let me start with then the floor systems. Typical floor systems, I mean, there are different kinds, of course. One-way floor system is your one-way slab and beam, which is what you have in your project, and also the one-way joist floor, which also you have in your project. Now, the one-way slab and beam, the problem with that is that as you increase your length, you're going to increase also the weight of the system. Okay? And it's not recommending to have, I mean, spans greater than 20 feet. So your slabs, okay? We're talking about the slabs. So the slab, no more than 20 for typical buildings. Now, you may have a little bigger in some bridges, but not very common, okay? You provide continuity, okay? Continuity of supports. Then you probably could increase that to 30 feet, right? Because now you have like both end continuous, right? And if you have both end continuous, then you can have 30 feet controlled by smaller spans on the ends, and that will allow you to have a good system. Okay? The one-way joist floor is pretty good. I mean, very effective. It's used a lot here in San Antonio. It spans, I mean, long. I mean, 50 feet at least. You can get 60 sometimes, but 50 definitely. Okay? You can use a standard joists, or you can use what is called a Y module, or also known as the skip joist system. Standard joists are economical for spans between 30 to 35, and then the Y module is the one that takes you to this 35 to 50, which are really very economical. And so some of these I have here some pictures. So here is your slab and beam system, right? And let me see if I can do something like that, right? And so you can see here is your column, and this is your beam, that is your frame beam, right? This will be now your interior beam, right? Interior beam, framing into another beam, right? But this is the typical. So this is the one with, but I don't know, you may have 2 interior beams, maybe another one here, but at least there is one interior beam, right? And your slab goes between beams, right? So that's the span for your slab. The other system is your standard joist, which is this one. This one I took it right in the tunnel by the engineering building, right? And notice the spacing, I mean, very narrow. Okay? So you're looking about 3 feet, okay, in general. Then you have your skip joist, and these also here in, this is by, yeah, also the tunnel, but near our building, right? And notice the space, a little bigger, right? Also notice the size of the beams, right? The beams match the joists, right? Very important on joist systems. Right? So that's your one-way floor systems. Then, of course, we have other types of floor systems that we are not going to cover in this class, but is the two-way floor system. And this is the two-way slab with beams. So that means you have beams in both directions, right? Pretty good too. I mean, it spans 30 feet, which is very good. But you have beams in all 4 sides, right? Now you happen to have a ratio, a span. Remember that a span to short, a span not exceeding 2, right? Then you got a two-way behavior. Right? You have more than 2, then you can treat it as a one-way system, right? So this system is not very common anymore, but it's there. Now, the ones that are very common now is this flat plate and this flat slab. The flat plate spans up to 30 feet, here is mentioned. There are no visible beams. There is no beams in the system, right? The most economical range really is 15 feet to 20. The flat slab is very similar, okay? But usually they have a thickening of the slab around the columns, normally called a drop panel. Okay? You can get up to spans of 35. Typical range is 20 to 30. And then you have the waffle or two-way joist system. So you can have your joist in two directions. And that one spans pretty long too. 55 economical range, 40 to 50. So what are these two-way slabs? So here is one. Okay? Notice there is absolutely no beams, only column slab. Okay? This one right here is your flat slab. Okay? So flat plate and then flat slab, because right above the column, right, you have this thickening of the slab. Okay? And the reason we do that is because in two-way slabs like this, flat plates and flat slabs, the shear, okay, the two-way shear is very critical, okay, very critical. And that's why we had to reinforce, put some extra reinforcement. This one, it looks like it doesn't have anything, but it may have lots of reinforcement around the column, because of that two-way shear. And here is a joist, a two-way joist system in both directions. I mean, this is nice because you can do a lot of architecture, can do a lot of fixture here. You can do very nice things, but it's very expensive and lots of forming, so it's very difficult. Right? Now here is one, you may have seen it. This is just across our building, right? It's pretty complex. Look, it has two-way joists. It has one-way joists. Notice that the spacings do not have to match, so you will worry about that in your building, right? No, I mean, this is your 5 feet, and then here's only 2 feet, right? And then here is that's probably also a joist system, but it could be a beam system, right? But most likely it's a joist system, it's a skip joist system. Right? But you also have slabs, right? So how about this slab? I mean, is it going this way? Is cantilevering both ways, right? So here is probably some two-way system here, probably one-way system here, solid slabs. So this one we have lots of different floors in there. So in a building you can have that. Okay? So it's not just unique like you have it in your project. I mean, that's kind of ideal, very nice, right? Real life, I mean, you can have different things. Okay, so let's go into the one-way slab. So the one-way slab, first thing, of course, we need to find our thicknesses, right? And again, this table right here, you have seen it, very similar when we use the beams. Well, ACI 318, say table 7311, has these values for slabs. Same as the beam, but different coefficients, right? Different coefficients, but same idea. So we already know what this means, hopefully. And then, of course, there are the corrections for yield value and for concrete weight. Right? So same. In addition to this, you also have to consider other things. For example, fire protection. Right? The code requires it. And so you want to give a 1 hour protection, depending on the aggregate that you're using, you will need certain thickness. Okay? Typically, we are here. So you don't put anything extra. For example, you will need at least, in a regular slab, 5 inches, basically, as a minimum, to have 2 hour fire resistance. Notice this, that the lightweight concrete needs less, 4 inches average, right? You can say average 4. So why? Because the lightweight concrete does not transmit heat as much as the regular concrete. Okay, so that's why you need 4. Now, what does it mean by 2 hour, 1 hour, and all that? Okay, 1 hour fire rating means that it will take 1 hour for the temperature to go to up to 250 degrees Fahrenheit on the opposite side of the fire. Okay, And so that's important. Okay? So if you do not have the concrete just exposed, because in that case you need like 5 inches, but you protect it with some sealing material, like a gypsum, plaster, and all that, then you can reduce the thickness to 3 inches. But you have to have a 1 inch ceiling. So that way it takes a little bit more time to get there. But that's more into the IBC. Normally your architect kind of checks that, but you have to to have exposed concrete, you may want to double check it. Okay, in general. Okay. Now, the way we specify slabs is that your slab is no more than 6 inches thick, then you can go by quarters. So I can have a 5 1/4 slab. Okay, I can have a 5 3/4 slab. Okay. If you go past the 6 inches, most common you will find that they go by 1/2 inch. So 6 1/2, 7 1/2, 8 1/2. Okay. This is important when you're designing joists, basically. Right? Joist, because that's how you do it. They can have a joist. You don't have these nice depths, right? Like 22 inches or 20 inches. It can be 18 3/4. Okay. All right. So how we're going to design? Well, you have to do same as in beams. You have to check that you satisfy moments and you satisfy shears, and of course serviceability, right? Serviceability. That means deflections and cracking control. It's a minimum. Right? So we're going to look into that. The phi factor goes with the same as your flexural elements. So we're looking again at the 0.9 for bending and 0.75 for shear. Right? How do we design this slab? I mean, we kind of gave that concept in chapter 5, right? So we talk about it, and we said everything is done per foot. That's exactly what it is, okay? You are going to design per foot. This 1 foot becomes the width that you're going to use. Okay? So in your formulas for bending, that's your width. Okay? And for analysis, you can use the simplified method in ACI 318 section 6.5. What is that? Oh, come on, you know that. You already know that, right? We've seen it, right? 6.5, we've seen it already, right? You've been using it, hopefully correctly. All right. Okay, so let me see here. Let's do 150. Okay. All right. Remember these coefficients, right? Okay. So that's what 6.5 is. Okay? So you know now how to use that, and this is typically what we use for the analysis. Okay, in this lab. All right. All right. So main reinforcement. We've been through that also in chapter 5, but kind of a review here, right? The main reinforcement is, of course, parallel to the span of the slab, so that is between beams, right? And in order to determine that, you will use area per foot because you're designing for 1 foot, right? Then you find that area per foot and you select the bar, okay, to get a spacing for that bar. The bar usually is less than, in size, is less than what you get here. So you get S's that are less than 12 inches. And you're going to see that in a minute, why we need S's less than 12 inches. So AS then is your area that you need, AB is the bar that you select, right? And S is the spacing of that bar that you're going to use. You need to check minimum amount of reinforcement, 7611 in your code. There's only one formula. is different than beams. Do not use the formulas for beams, okay? This is different. It happened in the exam. I gave you, I asked you for the minimum, and someone said, oh, I cannot find it because I don't have my D value. No, you only needed is the B and the H, okay? So be careful with that. This is different than beams, and it is shown in 7611. So we go back to the code, chapter 7, 7611. Okay, I think it's here. Okay, let's see, 7611. Okay, right there. Okay, so there it is. Okay, only one formula. There used to be 3 formulas, not anymore. Not anymore. So you're looking at previous exams, you're going to see that we use different formulas depending on the type of steel that we had, but not anymore. Now we only have one formula. Okay, one formula. So remember, when you're looking at previous exams, they were solved for other codes. The codes at that time, they used to have more formulas for the minimum. Now we only have one. Okay. So actually you need to remove this because that's not correct. It doesn't say that. That used to be the case, not anymore. So now it's valid for all steels, pretty much. Okay, so here is a beam, right, with interior beams. So here is your frame. So that's your frame, your columns, right, and your interior beams. So your span is here between beams. Right? So these are secondary beams. This is your primary element, right? You know that. So what else we need to do? You need to check the spacing of your bars. You cannot exceed 3 times the thickness of your slab or 18 inches. So unless you are using a very shallow slab, this will not be a problem. Mm-hmm. And then you also have to make sure that you have a value of S greater than 1 inch. This would be of 4/3 the diameter of the aggregate, right? Otherwise, I mean, your concrete may not flow through. Mm-hmm. And so all those things are in ACI. So let's go to the first one. It's 7723. So you go here, chapter 7, 7723. So here's 77, and there is 7723. Okay. So for non-pre-stress, that's what we're doing. Non-pre-stress concrete. Okay. And this right here refers to pre-stress. By the way, for those that may need a graduate class or may need an elective, right? You're looking for an elective. Pre-stress is going to be taught next semester, okay, the fall. And then we will learn about these things, okay? But for now, you're just doing this. Okay? Non-pre-stress. And that's 3H and 18 inches. Okay. All right. All right. So let's then go here. Oh, on this one, 25-1 is the other one regarding the aggregates, right? And this apply also to your beams too, right? So 25-1. So now we go here, 25-1. Okay. So 25 to 1 for parallel, non-pre-stress reinforcement, right? In a horizontal layer, so beams and slabs, right? Clear spacing shall be at least the greatest of 1 inch. This will be of 4/3 the diameter of the aggregate. All right? So it is. Shear reinforcement. Okay. If VU is greater than phi B sub C, then you should provide at least the minimum amount of shear reinforcement. Right? You may need to find what you need really, but in general, you should have at least the minimum. Okay? Now, most slabs, right? Most of the slabs that we know that you would in office buildings and all that do not have shear reinforcement, which means that you are not satisfying the minimum, and you have to use this formula to calculate your V sub C. Okay. All right. And so, remember, we have done this, we have practiced this. Some of you can make a mistake. I think some of you made mistakes on the homework on this, right? On the quiz too. Because you do not use minimum, you have to use the third formula in the shear, and it has this shape factor that will bring it down if your D value is more than 10 inches. Right? And so that's very important. So let's review that. 22551. So we go here, sectional method. This is where you have the design formulas, at least the few that the ACI wants to show you, right? So here's your bending, of course your beta, we did all that. So your axial loads, like shear, right? We started there. Maximum values, limits. Limit on F prime C, so we have all those remain the same. And here are the three formulas, right? So this is the one we're using because we are not satisfying minimum requirements. The moment you start putting reinforcement, then you have to move here. Okay? So it gets a bit more complicated because of that. And the problem with this is that these formulas were mostly developed for beams, and now we extend it to slabs, footings, walls, and so it creates a little bit of an issue because some of those elements, footings, walls, and slabs, one-way slabs at least, do not have shear reinforcement, so they kind of push you all the way here. Okay? In beams, you are mostly here. You normally will put that minimum, except certain sections, but I'll show you in chapter 9 how we're going to take care of that. But we're going to be here pretty much when we deal with beams. Mm-hmm. All right, so that's that one. Now the problem with this, of course, is that you're going to use this formula to check your shear, but you're trying to design, so that means you don't know what this is. So you want to take a very conservative approach. I mean, this is conservative, okay, very conservative. You assume that your raw value is based on number 4s at 12 inches. Okay? And again, because this formula was tailored and developed for beams, this raw W is area of steel divided by B and divided by D, okay? No H, but D. But however, we're using H to find the amount of steel when we deal with concrete, or we deal with the slabs, right? So that's what it was here. And that can get confused, right? But the raw W is based on BD, because I was set up for beams, okay? So it's BD. So you need to find the D value that is slab, and you do have the width, which is always 12 inches, right? So that's it. All right. The other thing that you have to place on the slab is this temperature and shrinkage reinforcement. This one is perpendicular to your main bars. Main bars. And it happens to have the same area as the minimum. And again, I had to remove this because that's not true anymore. It's valid for all steel now. There is only one formula. It used to be more than one formula. So you look at previous solutions for exams, you may have a different formula than this one. Now, for temperature is only one formula too. Okay, and that is on 24432. So serviceability, right? So around here someplace, let's see. Okay, if shrinkage and temperature movements are restrained, the effects of the tension force has to be design force. So you don't allow that movement, right? The concrete won't try to shrink, but you don't allow it, then it creates a tension force. That's what it means. Okay, you have to design for that. But really what we're looking at is this one. The ratio of the form, shrinkage, and temperature reinforcement area to gross concrete area, that's what we use B and H, shall be greater than or equal to 0.0018. The spacing of this reinforcement, right, should be 5H or 18. Which is here, all right? Now the space. Cover. The cover is the same in section 25131. We've already seen that table too, right? And so we have that. So we go to here. All right, let's see if I got the right table. Remember, there are several tables of this, right? Okay, so this is cast in place, non-pre-stress. So there it is, right? So slabs, right? There it is. Number 11 bar and smaller, 3/4 of an inch, 14 and 18, 1.5. That's non-exposed to weather or in contact with ground. Now you cast against this, you still got 3 inches here, you have all this here, that's still the same, okay? But this one is specifically for slabs. You have the beams, the columns, and then the slabs, joists, and walls are here. Here there is no difference. Okay, if your beam is touching the ground, right, and it's permanently in contact with ground, or your slab is doing that, or your footing is doing that, this is your cover. Okay? No matter what. Okay? That's good. All right. So that's that one. Okay. So you're exposing the weather again to weather in contact with the ground. You have a 1.5, 2 inches. Right? Now, this one is different. This is for fire rating again. Okay? So fire may control your values. Yeah? You can have a 3/4 inch cover for 1.25 hour fire rating. But you're going to expose this slab, it's not going to have any other protection, right? And you need at least 2 hours of protection, then that will not do it, right? And even 1 inch will not give you 2 hours of protection. So you may have to go to 125 or 1.5, and that will have enough cover to protect your bars from failing. Okay? All right. So fire requirements may change these minimum values. But normally, I mean, we have this slab protected by the ceiling material and all that, so we use these values. But if there is no protection, it's completely exposed, be careful with fire ratings. Now, general requirements. Use number 4 bars or larger for the top flexural steel. Okay. Number 3 could be used for very short spans. and shallow slabs. Mm-hmm. So, like for example, your joists, right? You can use number 3s. You need to do that. As a minimum, use number 4's 12. Mm-hmm. And that's because workers step on this thing, and so you don't want to bend the bars. So that number 4 is a 12. So that's why the number 4 is a 12 that I use here, right, comes from. Because that's the minimum you're going to use. And you cannot use anything lower than that. It would not be good. All right, so that because you are not going to use anything lower than that, then this is going to be very conservative. All right. The other thing you want to do is add some bars, right? Just do the number 3s and number 4s at 12 inches at the top of the connection of the slab and the negative and the beams, excuse me, the slab and the beams, right? But not on the on that. This is for the negative moments that may be developing on the same direction of the slab. Okay, so that's because remember your slab is going to have beams in four sides in general, unless it's more like a bridge, right? But if it's not a bridge, it will have beams on 4 sides. 2 sides, right? So let me go back to this figure. I think that probably be best, right? So you're designing in this direction. So the rebars that go on top of this beam will be designed based on their negative moments that you calculate for an analysis, right? We're assuming that there is no negative moment developed here between the slab and the beam. Okay, because we're assuming a one-way deflection, right? One-way direction. Well, that's not possible. I mean, it's hard to have a one-way deflection near this beam. So it's going to develop some kind of negative moment, very small, but it has some moment. And so what they're saying is that in this area, on these locations, okay, on top of the beams, you want to put number 4s at 12 or number 3s at 12. Just to protect for that negative moment that will develop because there is no a true one-way transfer load here. Okay? All right, so we come in here, and this is it. So now we can start doing the design. Design example here, we're going to design a cantilever concrete slab. Some deflections will not be computed, right? Nominal dead load 15 psf, not including the slab weight, right? And it should not always tell you that, I mean, because a slab, even 4 inches will go past that number. So you should know that this one does not include the weight of the slab. Nominal live load 100 psf. The cover is going to be 3/4 of an inch. Your F prime C is going to be 5,000 and your Fy is going to be 60,000. Okay? Span length equals 12 feet. And then you're going to sketch your solution. All right. So we're using that table, remember, 7311, simply supported, right? Oh no, cantilever, excuse me. So this one is cantilever, cantilever, so it's L over 10, right? For joists, it was L over, it could be for beams, it was L over 8, right? But for slabs, L over 10. So this slab is span 12, so 12, change it to inches. By 10, you need 14 4 inches. Just to give you an idea how thick you need to have a cantilever beam working as a one-way system. Okay. So we're going to use 14.5 because remember we can go by halves, right? So weight of this slab, 181 psf, right? Pretty heavy. So we add that to our dead load. We check the load combinations, and of course this one controls. So our load is 0.4 kips per square footage. Why is not, I didn't show it as kips per foot is because I still haven't multiplied by the tributary width, right? And how much is the tributary width for the slab? Right here, 1 foot. So it's really the same number. You're just going to multiply by 1 foot, and they make it 0.4 kips per foot. Yeah? But everything was, all these values were in per square footage. So your value here is per square footage. When you multiply by the 1 foot, then you make it per foot. Then you go and find your moments, right? Cantilever, WU, length square over 2. And so we'll replace the numbers and get our moment. This is per foot of slab because you're designing for 1 foot. And then your shear, right? Cantilever again. So, the thickness has to be deep enough so you can carry the shear without reinforcement, right? So we have then a 14.5. We're going to assume that we're going to use number 8 bars here. So that gives me a 13.25 for my D value. This is an assumption, okay? Remember that we don't know these values, so we can kind of guess here a little bit just to give us an idea how we are doing. We need to know the rho W, but we don't know it, so I'm going to assume the lowest possible, very conservative, 0.20 per foot, right? So that is my foot, that is my D. So I found as 13.25, so it gave me this number. Then I have to check for the size effect factor, right? I got my D at 13.25. I didn't use the most conservative value here because I'm using a number 8, right? So notice here the contradictions, right? Number 4, number 8. But doesn't matter here because we just, at this point, we're kind of guessing, right? Guess estimating, make sure that we're okay with the shear, we're not way off, right? And then we can do, when we finally got our values, we can do the real calculation. So here I can do also so I can do the number 4s and will give me a larger value, and it will give me even a smaller number here. Okay? So that would be even very, very conservative. Let's see the kind of okay. So because this is very conservative already, so doing this also conservative a lot. Okay, so I don't want to do that. So when we do that, we find our value is 765. Our shear is 4.8, 765. We're still good. Okay? Even with the reductions is good. Even I think if we get this one to be 0.9, we're still good. Okay? So usually then shear is not critical in one-way slabs. But these factors, reduce your shear significantly. Okay? All right. So now we're going to design. So this is a top mat, negative moment, right? Because it's cantilever. So I find my equation for the moments again. I replace this with 0.9D, find my area. With that area, I go ahead and find my A. And with that A, I found a new area. Or you use the quadratic equation. And so this is my area per foot, right? And some possible choices would be I can use a number 4, a number 5, or a number 6. In general, as I mentioned before, it is best for the case of the main bars to select a bar size that has an area less than or equal to, right? Now that I say that, right? Here it is. Less than or equal to the required area. So this is 0.49. You want to pick a bar that has an area equal to this or less than this. And so these are the three options. Okay. Because you want your spacing to be equal or less than 12. And we're going to see that in a minute why. Okay, so if I use number 6 bars, which is the 0.44, my spacing is 10.8, which I will round it down to 10. Okay, so I'm going to put then number 6s at 10 inches. All right. So now how much I'm providing. So make sure that this is where you started. This is your required value, right? Which was this 49. But you're going to put number 4s Now you put number 4 at 10.8, you're getting exactly this. But because you're putting it at 10, this is going to change now, and you're going to become your provided per foot. You need to have that number. So the provided area per foot is going to be my 0.44 at 10, but then I want to know what I'm doing at 12. And so that's now 0.53. It makes sense you're putting a little bit more. Why? Because you have reduced the spacing, right? That means you're putting more area than what you needed. All right, so there is my value. I check my minimum, right? It's BH based on the gross value, right? And I get 0.31, so 0.53 is good. My spacing, definitely good. And 10 inches is way below this 18, so we're good. So number 6 at 10 inches on centers. So now we're going to do the checking, right? Phi value 0.9, we're going to find the actual D, the T value, so that means my A value. So with my A value, I find my C, with my C and D sub T, I can find my phi factor. So it is 0.9, so that's good. And then I replace my values in the equation, the same that we done for the beams. And yes, we can carry them on. So number 6 is a 10 for main reinforcement, right? Now this reinforcement needs to satisfy cracking control. In the case of slabs, this is critical. Okay. Why? Because you're having spacings this much, 10 inches, right? 12 inches. So that's big spacing. So you want to make sure you satisfy cracking control when you're looking at slabs. In beams it was different because we know, we're going to get 4 inches, 3 inches, so that's pretty easy to check. But here, you can have large spaces, okay? So, cracking control, this is what we have. So this is the longitudinal view your beam cantilever, bar on the top. And then this one is a cross section of the slab, okay? With your bars coming out of the paper, right? All right. So according to the cracking control, we know these formulas. We have used them already. We need to find the C sub C. In the case of slabs, there is no stirrup, right? So the only thing you got is the cover. So C sub C is 3/4 of an inch. We're going to assume the simplified method by taking 2/3 of Fy. And so we put the 2/3 of Fy, we use 3/4 of an inch, 13.1 we get here. And then this one for grade 60. For grade 60, okay? You always get 12 inches. So this is the reason, right? This is the reason why I said, right? When you select your bars, pick a value less than this, so your S doesn't go over 12 inches, because for grade 60, the smallest value is going to be most likely that 12 inch, okay? So you don't want to exceed 12 inches. Now it can be worse. You are using like a 100 KSI steel. Mm-hmm. But for 60, 12 inches. Okay, 12 inches is your value. So you have to make sure you do that. Okay, so now that's okay. Satisfies cracking control. We're good. All right. Then I'm going to do my temperature. Okay, here's my temperature. Boom, 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 boom. All right. Temperature, shrinking reinforcement. Right. So there is nothing to calculate. You just have that. Now here you can exceed the 12 inches. So now I can pick a value greater than this. So I'm going to use again my number 6s, which is greater than that, gives me 17. The maximum spacing is 18, so 17 looks good. Okay? So 17 is there. For convenience, I'm going to change my number 6s to 9. I'm under 6 to 15. Now, why is that? Simply because, in the field, right? The guy is going to put this 6 and 9 inches. You do 10 inches, then you have to measure 10 inches, 10 inches, 10 inches. Right? If you do 9 inches, they say, well, that's a multiple of 3 inches. They kind of know where the 3 inches is. So they go 9, 9, 9, 9. So a lot easier, okay, than 10s. The same with the 15 rather than 17, right? It's a multiple of 3 inches. It's a lot easier to visualize in the field. So that's the only reason. Now, because I'm putting now number 6 and 9 inches, what happens to your compression force? Yes, it's going to increase. You're putting more steel, right? Oh, that means I have a bigger C value. Oh, that means your maximum may not be satisfied. Well, let's look at that again. Go back here, right? And notice that we always, way below the limit, okay? So that change will not hurt you anything, okay? We are way below the limit. Now, you're very close to this limit. You have to recheck it because you are changing your compression force, right? All right. So that takes care of the final design. Now we're going to do a simply supported beam, right? It's going to be lightweight concrete now. And I specify here your weight as 100 pounds per cubic foot. Okay. So we're going to have a live load of 250 psf. This is for a warehouse. Okay, heavy load. Cover 3/4 of an inch. There is your concrete. And the span length is 20 feet. Oh, we're using grade 40 steel. Okay. So we find our H miniman, and we're using the L20, okay, for simply supported. This is the correction for lightweight concrete, and this is the correction for the 40,000 psi. So after all that correction, I need 11 inches. And I said, I'm going to do 12. Okay. You can use the 11. That's okay. I use the 12. Okay, and this is something that you're having issues in your beam design, right? You're getting the numbers and you say, okay, well, I have to stay with that now. No, I mean, you can vary your values, 1 inch, 2 inches, right? To accommodate. The value is just the reference that you have to design your beams. The same here. This is a reference value. It doesn't mean I have to use that value. If I use less, all it means is I have to check deflections. If I use more, well, with more weight, maybe okay. Now, in slabs, probably going 11 to 12 may not be a good idea, especially in economy, because you may have a big slab, lots of concrete, right? And so even though it's 1 inch, 1 inch by, another 3,000 square feet or 40,000 square feet of slab, right? It's all the concrete. And so you may want to consider maybe 11.5 or 11. Yeah? So that'll probably be something closer. All right. So then is the economy point of view also plays on deciding these things. Right? Small slab, I can probably do that. If I have 40,000 square feet of slab, right? Then this 1 inch increase is just a lot of concrete. All right. Okay. So weight of a slab, 12 inches divided by 12 is in the feet, multiplied by 100, so it's 100. Okay. My day loads, my live loads, my load combinations, and the 1.2, 1.6 controls. I had to check my H miniman for shear. So here is again the formula. I'm assuming now the worst case possible using number 4. There it is. Just to show you, that you don't have to, you're just guessing, okay? And so you're just picking values and you're just guessing. But that's just to be conservative. Okay? Again, number 4 is a 12 to be conservative. That gives me a raw value very low here. Because I'm using 12, right? That gives me a D value of 11, and so now is there's a lambda S factor that needs to be considered. Okay? So with that, we find our shear got pretty low, right? But we use is 5.5. So the H minimum in this case, like, it got pretty bad, right? It got pretty bad. So So you would say, well, gosh, I mean, that's bad. So that means I need to make it even thicker. Okay. But the difference is not too bad. I mean, this is almost 5 and this is 5.5. So we're close, right? So if we use something else than number 4s, right? Then this is going to be better. It's going to be bigger, right? This one is going to be smaller, right? And so then this one is going to be better. So both factors are going to increase, right? Since only need, 10% increase, that may be enough, right? So then I just keep it like that, and I'm going to check it later, make sure that it works. Okay. So find my moment, simply support it, 27.5. Go ahead and set up for finding my area of steel. B is going to be, of course, 12 inches. So we got that. Find my A value, find my area of steel, right? So I need 0.87 per foot. My minimum is 0.26. We're good. Spacing, 3H, 18 controls. We are doing, we don't know yet what spacing, so let's see. We're going to use number 8 bars. Okay. Why? Because we are at 0.87. So I can use number 8 because it's 0.79. I can use number 7s, I can use number 6s, I can use number 4s, I can use number 5s, right? Anything below 8 or below I can use. So try number 8 bars, and I do that. The spacing again, 10.9, I go to 10. Okay? So if I use number 8 at 10, my S that I'm providing is different than my S required because I'm not matching the number, right? So I get 0.95, so I'm putting more, right? Now we check our D, that's 1075 here, based on the number 8, right? Find my A, find my C, C over D sub T. Again, notice that this is way below this number, right? So in slabs, you got lots of utility. So we satisfy A's maximum, we satisfy the phi factor 0.9, we find our value, and we carry the moment. So no problem. Okay? Next, we have to do cracking control check. Okay. So again, we go here, same formula. Now, this is simply supported, right? Main bars, and these are the bars that you see you make a cut, right? So you make a cut, then you will see the bars like this. All right. So here my cracking control, I get 26. Here, because it's number 40 now, I'm getting 18, right? So 10 is okay. So 18, that's good. All right. Temperature and shrinkage, same formula. So I get that I need 26, that's the minimum. I go and find my spacing, I'm going to use number 6 bars. I got 18.2 with that. I cannot go past 18, so I'm going to say 18. And 18 works. So my final design then has the 8 number 10s, 8 or 10, and then the 6 at 18. Now I could change this one, number 8, a 9, right? If I feel like that is best for construction, right? So I mentioned that here, right? So you can do that. It's multiple of 3. Again. Also notice that your temperature here goes on the inside of your main bar. So let's go back here, right? Cantilever in the inside, never on the outside. So your temperature bars are not on the outside, it's always on the inside. And they are perpendicular to your main bar. Okay. So temperature bars on the inside, perpendicular to the main bar. Okay, now we're going to recheck this here because we didn't pass, right? Remember. Okay, so we're now doing A number 10, so now we have a good number. So we got this area provided. we find our rho W based on ASBWD. So now we got this one. The lambda S is here. So we put in the formula. Oh, see, look, now we got 6.6. So greater than the 5.5. Mm-hmm. So our value was really, very conservative. But that gives you an idea, at least, on where you stand in terms of your numbers and how you can check them. You know? All right, so that takes care of that, and so verifies our designs. Okay, so I'll stop here, and we'll continue with T-beams next time.